Hey everybody, so welcome to Linear Algebra. Today we're going to actually go straight into a more difficult video. We're going to actually start doing some proofs here. And the reason is I want you to immediately get hit with the fact that in college, you're going to do a lot more than just solving math problems. You're actually going to have to do a lot of proofs, and you're going to have to memorize a lot of proofs, especially if those of you who consider going into graduate school, and this is going to likely be the case. So I'm going to start with some very, very fundamental ideas here. So the definition I'm going to just start with and just hit it to you right off the bat is that we're going to let A, B, and C all be n-tuple, and I'll explain to you what this all means in a second, sequences of n real numbers. And an example of this would be, so something like A is equal to A1, A2, A sub n, and B is equal to B1, B2, B sub n, and you get the idea, okay? And yes, I'll make this a little... Hopefully you guys can, something like that. Something like that. So this is completely wrong here, but you guys get the idea. So this part is just wrong. This is supposed to be B. Okay, well, what this is, what we're dealing with here are points and vectors. And most importantly, just points right now. And from this definition, which kind of gives us an understanding of what points are. Because in the two-dimensional plane, which we denote by the real number squared, what happens is that, of course, we have a coordinate system where we have, let's say this was, point A, it's 2, 1. Well, this is all great, and this is quite simple, and we can do a lot of things here. But when we kind of shift our dimension to something a little more abstract, a little more complicated, something like a 3D dimension, and we want to, this point right here, which hopefully you guys can see, it's like pointing into you. It's like me going here, here, and like that. And you can kind of see the point here, something like that. So this is this edge point here. We now represent this as a point with 3 coordinates. Let's say this is like 3, -1, 3, or something like that, okay? So we now have 3-dimensional things to talk about. And from this definition and using this definition, we can now kind of extrapolate and come up with some pretty nice conclusions that you guys already know. And we're going to prove them now and kind of use that definition. And so get used to really working these problems out, okay? So the first thing we're going to prove now is that A plus B is equal to B plus A. So these are 2 points that adding these 2 points are commutative. So point adding is commutative. And this, of course, and some other things we're going to use here is that we know that the real numbers are commutative, associative, and ... Lots of great properties. All of them things, distributive property, they're all going to work, okay? But we need to prove that they work for points, not just numbers. So the first step here would be to write A plus B as A1, A2, ... A sub n plus B1, b2 dot 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 a sub n. Now remember, when we had points like 2 comma 1 plus 0 comma 3, we would just add them respectively, so we would get 2 comma 4, right? And so we're going to take that idea and we're just going to apply it here. So this is the same thing as a1 plus b1, a2 plus b2 dot 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 an plus bn. Now remember, in the definition up here, each of these are sequences of n-tuple sequences of n real numbers. So all these a1, an, bn are all in the real. In this case, it would be the second dimension, r squared. Or they're just real numbers. Sorry, we don't need to include the r squared. That's a space we're going to work with when we're going to talk about L2 spaces in a second. So because of that, we know that real numbers are commutative, and so this is the same thing as just b1 plus a1, b2 plus a2 dot 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 b sub n plus a sub n. And there you have it. We can now just separate this back into the original sum, which is just b1, b2 dot 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 b sub n plus a1, a2 dot 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 a sub n, and this is of course equal to b plus a, so it is commutative. We are allowed to do this again. Okay. I know it's going to seem so stupid, like, yeah, obviously it's commutative. But without being able to prove these things, you're not only going to have a lack of understanding of how to prove harder questions, because imagine you didn't know something that seems so fundamental, right? Calculus, all of you have learned it, and you're like, of course, right? It makes so much sense. But to come up with something like that takes a lot of outside thinking, a lot of fundamental thinking. So this is training you guys to think in more proof and more abstract ways, to really dive into how we came up with maths so that we can come up with new maths. For the second one, where there's going to be 8, by the way, it's going to be the associative property that this is true. Okay? So the way we're going to do this is, and let me just fix the audio. So here's how we're going to do it. We're going to start the same way. A1, A2, dot, 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 A sub n is equal to plus B1, B2, dot, 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 B sub n. But of course, plus C1, C2, dot, 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 C sub n, all under these brackets. Okay, this is the same thing. Okay, so we're going to have A1, A2, dot, 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 A sub n, plus, and we're going to combine the inside sum now, as we did earlier, into B1 plus C1, B2 plus C2, dot, 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 Bn plus Cn. Okay? We can now combine this once again, and there shouldn't be a parentheses here. Just be B1, like that. We're going to combine these two again. Say this is equal to big brackets A1 plus B1 plus C1, comma A2 plus B2 plus C2, comma dot dot dot, A3 or AN plus BN plus CN. Okay, so this is the same thing. This is all a coordinate sequence of n-tuple sequences of real numbers. Now, once again, we're going to use the fact that these are all A1, so A sub n, B sub n, and C sub n are all part of the real numbers, which are associative. So it simply follows that we can just rewrite this ordered pair as simply A1 plus B1 plus C1, like this. A2 plus B2 plus C1 or plus C2, dot dot dot, A sub n plus B sub n comma plus cn. Wow, this is really annoying. And hopefully you can now see that this is just a way of saying a plus b plus c once you see how it undoes itself. So another way, very similar way to prove it, and this is kind of going to be the trend of what we're going to do today. The third property, which is a very easy one to prove, is that a plus o is equal to a. Now, in linear algebra, o is the origin, 0, 0. And so it's kind of like the identity that any real number added with 0 is that original number. So simply put, this is easy to prove. Just show that the ordered sequence of real numbers for each point added with 0, 0, 0 is just equal to a1 plus 0, a2 plus 0, and plus 0. And of course, this is just equal to a1, a2, a sub n, which is equal to a. So that's an easy proof to just quickly check off. You just show that adding 0 to a real number is what's going on within these points, and you're done. And of course, we're using these real number axioms, really, that assumptions that we just know that real numbers behave like this. So we're not going to prove the steps that are happening really in between here, but just know that this is allowed. For a plus its negative version is equal to the empty, not the empty set, the origin, O. So the first thing we're going to do is show once again the n sequence iterated form or something, plus, and I'm just going to skip the step where I write it, but it's going to be negative times every single step. So negative a1, negative a2, negative a sub n. And simply put here, this is just equal to a sub 1 minus a sub 1, a sub 2 minus a sub 2, a sub n minus a sub n, and of course this is all equal to 0, and so we just arrive at the original good old origin. Very easy. And I know this is going to seem very intuitive, very simple, very kind of stupid almost. But that's exactly why we're going to do it. So work through this with me. We only got we got 4 more. So let's go. Now we have d plus e times a is equal to dA plus ea, the distributive property. And d and e are just constants that are real. So just know that. So we're going to set this equal. So this is going to be d plus e times a1, a2, a sub n, which is equal to d plus e. So I'm going to rewrite this with large brackets. D plus e times a1 plus, comma, d plus e a2, d plus e times a sub n. Okay, we're allowed to do this to each term because remember, a scalar times a point is just each of the individual points multiplied by that scalar. And from here, it simply follows that we just have dA1 plus EA1 dA2 plus EA2 DAN plus EA sub n, and we're allowed to do this because the real numbers are distributive. Okay? This is of course just going to be equal to d times a sub 1, a sub 2, a sub n plus e times a sub 1, comma, a sub 2, comma, dot, 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 a sub n, because of everything we proved up here and all the properties we used up here, where we're allowed to split these sums as follows right there. We're allowed to split these into two different sums. And of course, there's a step that I skipped here, and I'll just redo it here, which was that we just rewrite it as dA1, dA2, dAn is equal to, or plus, EA1, EA2, EA sub n, of course. And finally, we just know that this is just going to be dA plus E times A, and there's the result that we want. Okay, last few are, well, this one's going to be a little long. We're going to show that dA plus B is equal to dA plus dB. And the only difference here is that instead of two constants being summed, we have 2 points being summed and multiplied by a scalar. So d times A1, A2, A sub n, plus, and I should put brackets like that, B1, B2, B sub n. Okay? So this is just equal to d times A1 plus B1, d A2 plus B2, dot, 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 d times AN plus BN. We're allowed to do this now and combine the inner 2 points and just multiply the d, the scalar, into each of the points. Okay? And now, as we did earlier, we just distribute the d scalar because we are allowed to do that since all the numbers d, A1 are all real. And real numbers are to have a distributive property. So this is just equal to dA1 plus dB1, dA2 plus dB2, dot, 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 dAn plus dBn. And there you have it. From here, all we do is now split this into two sums, into two separate points. So we have now dA1, dA2, dot, 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 dAn added with dB1, dB2, and dBn. Okay? From here, we simply notice that this is just going to be d times A1, A2, A sub n plus d times B1, B2, dot, 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 B sub n. And this is just d times A plus d times B. And so we are good to go. 2 more to go, guys. Let's go. Let's keep it going. Now we're going to prove that the two scalars like this are also associative within each other and multiplied by a point. So let me just write that a little cleaner. Not cleaner at all. So this is what we're going to prove. So it's just going to be d times E times A1, A2, A sub n. And we need to show that this is equal to d, or actually this is just going to be equal to d times EA1, EA2, dot, 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 EAN for obvious reasons. Now, these are all, of course, and this is just, once again, I should always state that these are all just in the real numbers. So they're distributive, and that's why that works. This is, of course, then just equal to dEA1. And I'm going to put a parentheses around the EA1 because we technically haven't shown it yet. So like this is really what's going on. And from here, well, we simply know that a product of multiple terms is always going to be associative. And so we can just move the parentheses around. So this is the same thing as DE A1 DE A2 ... DE A sub n. And of course, you can naturally see how this is just going to turn out. We can now factor out a DE from the entire thing, and notice it's just going to be a product, and this is just DE times A. So we're good to go. All right, one more. This is going to be the easiest one, maybe. It's just that 1 times A is just A, the identity, I guess, proof here. So it's going to be, of course, 1 times A1, A2, A sub n. This is equal to 1A1, 1A2, 1A sub n. And of course, for real numbers, 1 is an identity. For multiplication, so this means that it's just going to be A1, A2, ... A sub n, which is equal to A, and there it is. That's all for this video, guys. That's all the proofs that I wanted to go over today. This is just to get you guys started in the flow of doing the boring things, because now when we start doing actual proofs, or not, these are actual proofs, when we start doing more complex proofs where you have to think on your own, you're going to have to come up with creative solutions as the following here. So lots of proofs that we went over today. These are really cool to look at, memorize them, understand how we did them, understand the concepts that we've got them from, and there you have it, guys. Some basic fundamental properties of points. There you have it, guys, and I hope that does it for you. I will see you in another video, hopefully in the next video on the algebra, linear algebra course that I'm going to now have a playlist on. So see you guys then. Bye.